Okay, great. So I'm going to be talking about one possible technique for oversampling that you might have not heard of or considered is the SMOTE, what I like to call it, or which stands for the Synthetic Minority Oversampling Techniques. Don't know where the E is, but I guess it's the T and the E in techniques, but that's neither here or there. Um, yeah, so about SMO, essentially, I'm going to go through this example, and I think like examples is the best way of showing the power of such technique. But let's say you have a imbalanced class like this one. So we have a minority class. You can think of this as being one type of flower. And this is the sepal width, and this is the sepal length. So the red one is, let's say, some type of flower, flower one, and the green one is flower two. So we have four in the minority class, and we have about 13 in the majority class, something along those lines anyway. Um, and we want to make sure that it's somewhat balanced, because at the moment your model could just predict everything is going to be flower 2 because that's the majority class, and it will be accurate on most occasions because of just the nature of the population and how it is statistically distributed. It's like saying, I was going to say coronavirus, but I guess everybody has that now, so it's not the best thing. But maybe let's pick a rare genetic condition. I could that only affects 1% of people. If I was to if I was to say, yeah, everybody, let's just build a model that is really, really accurate. And let's say it affects 1% of people, which I guess is not too rare, but let's say your model just predicts that everybody doesn't have the disease. Your model will be predicting correctly 99% of the time. But would you say it's a good model? No, because it's just simplistic. It's just saying that everything is a no. So it's the same logic here. So your model could just be accurate, but it could be missing out on some of the important classification that we want the model to actually have. So what SMOTE is essentially is we got to get these minority class. We got to beef them up. We got to get more of these. One way of doing that is simply to imagine just putting some lines between them. Let's just imagine we're talking about um, this particular data point. We draw a line between this data point and this data point, and we let our model randomly predict a data point in between these lines. It could be one, it could be two, depending on uh, how many samples you want to put in each one, so that you could. I mean, if we was to do one in each line, we're gonna get about five new samples, which makes our minority class go from 4 to 9, which is improvement. But you might want it to be so that it's equal to the majority class, so you might put two in each line, so it will randomly predict maybe one data point is over here and one data point is over here, and it'll do the same for each and every single line there is. And then that would make it go from 14, it will go from a line of a data point of 4 data points to 14, which much better. That matches our majority class. Our model has a balanced data set, you could say. So it's depending on how many you want to put. Do you want to make it your minority class the same as the majority class? That could not be great in some circumstances. You would want it to be somewhat representative of the population. You don't want to just make it so that your model is going to be a bad predictor. But these are discussions for you to have by yourself, which I'm sure you're going to enjoy. But essentially, this is what it does. So it randomly picks these minority instances. So these red dots are the synthetically picked instances. So it has one data point there, one data point there, and it just done that. And here it created 1, 2, 3, 4, 5, 6, 7, 8. 8 new samples. 8 new samples with 4 data points. That's now 12. And this is matching up quite well with our majority class. So that's how it's done. It's essentially picking synthetic points in between our data points that already exist. So that you might ask why do this? Why don't we just randomly predict it? Because then it won't be representative of the minority class. At least we know that this is somewhat representative of the minority class, because it's going to lie in these boundaries, and it's not just randomly predicting it. And there is another technique called, I don't even know what it's called in terms of its abbreviation, but it's ADASYN. So essentially it's the same thing as this, except now instead of it being predicted on strictly these lines that we've drew up between the data points, it predicts, it does the same thing, randomly predicts between the lines, but then it will just maybe defer slightly away from the line. It might add it just adds a bit of variance to the lines. And the reason is because this stops it from your data points being linearly correlated between each other, which is important for foregoing some of the problems of having linearly correlated data points between itself, because then it's just it's very synthetic and it's not what you'd actually observe in nature. So it creates this sort of normal distribution between these lines, and it will predict it'll predict a point in that line. So instead of the red data point being over there, it might just be a tiny data point over here, let's say, or it could be here. It could be here. Or it could still be on the line, but it might be a bit off the line, somewhere like that. So it won't be just coming up on this line. It could be anywhere in between the lines, which is great. That added bit of variance stops it from being linearly correlated between each other, which is great. Great, and that's the two techniques, SMOTE and the ADASYN, that you might want to deploy in your cases of doing oversampling, depending on your situation. Thank you very much.